Hey everyone! If you're a junior developer getting your hands dirty with Go, or honestly, even if you've been writing Go for a little while and just want to really solidify those core fundamentals, you are in exactly the right place. Today, we're going to master a totally fundamental Go programming pattern. Think of this explainer as a patient, step-by-step pair programming session where we're going to level up your defensive programming skills together. But before we even look at a single line of code, I want to pose this question directly to you. How would you safely combine two slices in Go without causing a runtime panic? You know, the kind that triggers a 2 a.m. incident response call? And beyond just avoiding a crash, how do you actually do it in a way that respects the precise meaning of the data you're passing around? Try to get yourself into a problem-solving, defensive programming mindset right now, because the answer requires just a little more nuance than just mashing two arrays together. Okay, let's dive into this. Here is our lesson plan for today's explainer. First, we'll look at the concat slice solution. Second, built-in Go features. Third, adding the nil guard. Fourth, handling single nil inputs. Fifth, nil versus empty slices. And finally, sixth, exactly why this solution works.
All right, section 1, the concat slice solution and the final code. You know, I always find that seeing the final destination first really helps build a mental map before getting into the nitty-gritty details. So here's our complete nil-safe concat slice function. Take a breath and just look at it for a second. It is incredibly concise. It's literally just 4 elegant lines of code. It takes 2 integer slices, S1 and S2, and returns a single integer slice. It's just got a conditional check at the top and a return statement at the bottom. That is the whole shebang. It might look super simple, but there is a lot of mechanical beauty happening beneath the surface here. Let's deconstruct it.
Moving on to section 2, built-in Go features, deconstructing the tools.
We need to break down the specific tools and functions our solution relies on to do all the heavy lifting. The engine of our little function basically relies on 2 foundational Go concepts. First up is the built-in append function. This adds 1 or more elements to a slice and returns a potentially new slice, automatically handling the growth of the underlying memory array. Second is the spread operator, which is those 3 little dots you see at the end of a slice variable. This is absolutely crucial. It unpacks a slice into its individual elements so they can be passed as separate arguments. To really understand why that spread operator is necessary, let's take a look at the wrong way to do it. Notice that type mismatch error. If you just try to run append S1, S2 without the dots, Go throws a type mismatch error right in your face. Why? Well, because append is expecting individual integer values to add to S1, but you're actually handing it an entire slice of integers. Adding those 3 dots unpacks S2 into S2 index 0, S2 index 1, S2 index 2, and so on, which append happily accepts, totally regardless of the length. Section 3. Adding the nil guard and preserving semantics. This is arguably the most nuanced and important part of the entire code block we just looked at. If append is so incredibly powerful, here is a critical gotcha question for you. Why not just skip the if statement entirely and let append handle nil inputs natively? Seriously, think about it. Put on your mid-level engineering hat for a second. What happens to the actual behavior of your code if you just aggressively append everything? Now, what's really interesting here is the concept of semantic honesty. If we don't use our nil guard and we pass 2 nil slices into append, it technically runs perfectly safely without panicking. But look at the result type. It returns an empty slice. But wait, if we were given absolutely nothing, no input whatsoever, returning an allocated empty slice is pretty semantically misleading, right? It implies a collection exists but is empty. Our nil guard intercepts this and explicitly returns nil, true nothingness. This preserves the completely honest meaning of the data. All right, section 4, handling single nil inputs and safely falling through. So we know what happens when both are nil, but how does our function behave when only one of the provided slices is nil? Because our guard at the top of the function only fires when both S1 and S2 are nil, a single nil input actually passes straight through to our return append statement. And look at how beautifully Go handles this natively. If S1 is nil, append basically treats it as an empty slice and just returns a copy of S2. If S2 is nil, the spread operator expands it to absolutely nothing, and append just returns a copy of S1. It safely falls right through without us needing to write any extra clunky if-else branches. Let's rapid fire through this matrix of edge cases to see how this builds a completely bulletproof function. This proves the robustness of our code against all possible scenarios.
2 nils, the nil guard fires, returns nil. 1 nil, one populated slice, it returns a copy of the populated slice. 2 empty but non-nil slices, it safely returns an empty non-nil slice. By combining our specific nil guard with the native behavior of append, literally every single variation is handled flawlessly.
Section 5, nil versus empty slices, a really key distinction in Go. Listen up, especially if you're interviewing for a Go position anytime soon, because this trips up so many junior developers. A nil slice and an empty slice both have a length of 0 and a capacity of 0. When you range over them in a loop or append to them, they behave identically, but they are absolutely not the same thing. A nil slice equals nil, an empty slice does not. Why does this matter in the real world? Well, imagine you're building an API. If you use JSON marshal on a nil slice, it encodes as null in JSON. If you marshal an empty slice, it encodes as empty brackets. And I guarantee you, those mean very different things to a front-end client consuming your API. So, the absolutely crucial point here is this simple rule of thumb. Return nil when there is genuinely no result, kind of like a database query that found nothing. Return an empty slice when the result is an empty collection, like a user who has an active account but currently has 0 friends. Adopting this in your daily coding signals your intent so clearly to other developers.
Finally, Section 6, why this solution works, the summary.
Let's lock in everything we've learned during this explainer. Our 4-line concat slice function is pretty much perfect because it's idiomatic Go. It leans on append and the spread operator exactly as the language designers intended. It manually preserves the semantic difference between nil and empty when both inputs are lacking. It lets single nil inputs and empty inputs be handled completely automatically by the Go runtime. And honestly, best of all, we didn't have to write a single manual for loop. The runtime handles all the underlying memory allocation and copying for us safely. I want to leave you with one final thought to chew on today. How will you implement semantic honesty with nil values in your own Go codebase? Next time you open your editor, take a hard look at your recent API responses or helper functions. Are you maybe accidentally returning empty arrays when you actually mean null? Try to keep this defensive, intentional mindset with you as you code. Thanks so much for joining me for this explainer, and happy coding.